Welcome to Lecture 5.4, the Fundamental Theorem of Calculus. We're going to add a little bit more official definitions and a new formula as well. So the Fundamental Theorem of Calculus. So the Fundamental Theorem of Calculus establishes a strong connection between the two branches of calculus, which is differentials and integrals. And remember, differential calculus arose from the tangent problem, where we solved instantaneous rates of change, first with limits and then with simplified methods, or what I called earlier cheats, like you do in a video game. Whereas integral calculus arose from a seemingly unrelated problem, which was the area under a curve, or the net or accumulated change. It was actually Newton's mentor at Cambridge, Isaac Barrow, who discovered the connection between these, and that these were in fact inverse processes. So the fundamental theorem of calculus just simply says this: if f is a continuous function on an interval over ab, then the function g defined by the integral, the definite integral from a to x of f of t dt, is the antiderivative of f, that is g prime x equals f of x. And we know this, okay? We just saw this before. So you actually started out with this knowledge, which actually came later after the connection was discovered. So if we find the derivative, here's an example. So find the derivative of the function g of x from 0 to x of 1 plus t squared dt. So if we evaluate this integral, actually, if we just use the formula here, we can see that this just tells us that the derivative is going to be equal to the integrand, 1 plus x squared, the square root of, okay? And now, why is that? Because no matter what we plug in here, remember, if we take the integral first, this value at a constant is going to give us a numerical value. And so the derivative of a constant is 0. So we just get back to this upper integral value. Although the formula of the form g of x equals the integral from a to x of f of t may seem like a strange way of defining a function, because typically we've started out with the functions and then taken the integrals of their derivatives. Books on physics, chemistry, and statistics are full of such functions. For example, one function, the Fresnel Function, which is the integral from 0 to x of sine of pi t squared over 2, is named after a French physicist, Fresnel, who did a lot of work in optics. And it's interesting here, it's so curious how things used in one area of science can be applied in another. So this function first appeared in his theory of diffraction of light waves, but interestingly, now it's been applied to the design of highways. So it's quite cool that, and this is often where new discoveries come from, is applying applications in one field of science to another. And here we have an actual application from light waves to really a much more civil engineering approach, or the design of highways. Quite cool. So let's see how we can do this and solve an actual problem here with a function. So here we have g of x equals the integral from a to x of f of t dt, where a equals 1 and f of t equals t squared. So this will give us a problem that we can see that works out and matches the fundamental theorem of calculus. Find a formula for g of x and then calculate g prime x. So finding the formula for g of x is easy. We're simply going to plug in the values. A is 1, x is x, f of t equals t squared. So let's just plug this in and find the integral first of all, because g of x equals the integral. So the integral of t squared is t cubed over 3, simple integral, the antiderivative. We're going to evaluate that from 1 to x. So we plug in those values, so we get x cubed over 3 minus 1 over 3, which actually, this is how I would write this. I wouldn't write it like this. It looks like they tried to simplify it, but it's, we don't want to deal with a fraction. So let's write it as two different functions, x cubed over 3 minus 1/3. Well, the derivative of this is pretty simple to take. The derivative of the first piece. The derivative of the second, of course, is 0, so we only need the derivative of the first piece, which just gives us x squared. And you should be able to take that derivative, okay? So we can see that this is actually a good example that demonstrates that first property of the fundamental theorem of calculus. Okay? This is just restating that. So let's look at some examples. So let's find the derivative of secant t dt evaluated from 1 to x to the 4th. Now be careful, because at first it looks like it follows the first rule of the fundamental theorem, but notice that our upper limit is not x, it's x to the 4th, so it's a function of x. So we actually have a chain limit here. So we have to kind of do some substitution here. So we're going to evaluate it from 1 to x to the 4. So let's substitute u equals x to the 4th. So we get the derivative between 1 to u of secant t dt. All right. Well, we know that the derivative of this first part is simply secant u, but we also have to remember that this is an implied function of x, so it's secant u based upon the first fundamental theorem of calculus. So the derivative of this part from 1 to u is secant u, but we have to remember that when we're doing the chain rule, we also have to take the derivative of the inner. So we get secant x to the 4th times the derivative of the inner, which is x to the 4th, which is 4x cubed. Okay? So be careful with this. If you have a function here, you have to do some substitution, and then it follows the chain rule, remembering that we have to also include the derivative of u. Okay? Now this is another interesting piece, and this is one of the last formulas we're going to add in here. We know that the area under a curve and above the x-axis is given by the integral. Area equals the integral over the interval from a to b of f of x dx. Interestingly, this area is also the area of the rectangle with the base equal to the integral b minus a, and the height equal to the average value of the function over that interval. Okay? The average value of the function, or the average height over that interval. So the width times the average height actually gives us the same area, as you can see under here. So the area of A is equal to the area of A. Quite curious. So if we do a little algebra, so notice that the area divided by the average, by the interval, this will give us the average, right? Remember, we always take the average value of the function divided by the width of the function. The area divided by the average height will give us the width of the function. And this is really how we calculate averages anyway, right? The average of 3 tests is the score on the 3 tests, the total score on the 3 tests divided by the number of tests, okay? So the average value of a function is equal to the area divided by b minus a. Well, remember, the area is this function here. Well, 1 over b minus a is a constant, so we can pull this outside. So the average value of a function is 1 over b minus a, or 1 over the distance between a and b on the x-axis, right? The difference in x's, times the integral, which is the area function, a to b of f of x dx. Okay, so let's look at this for a rather simple problem, but that it's often confusing to interpret, okay? At least the difference in values here. Suppose that the cost in dollars for x table lamps is given by C of x equals 400 plus x plus 0.3x squared. What is the average value of C of x for 10 to 20 lamps? And then find the average cost per unit if 40 lamps are produced. So notice what we're asking in A is to find the average value of the cost over an interval from 10 to 20. So this is our formula, the average value of the function, the average value of cost, okay, which is not the same as the average cost per unit, Okay, so A is pretty simple. It just follows the formula. 1 over 20 minus 10, evaluating the integral from 10 to 20 of the function. This is simple enough to calculate. I'm not going to go through the steps. You should be able to do this, right? The integral 400x plus x squared over 2 plus 0.1 x cubed. All right? Evaluated at 20, subtracted the evaluation at 10, and then multiplied by 1 over 10. Make sure you can calculate this, go through the steps, don't just trust this value. This is good practice to try this average value. Okay, now B asks us to find the average cost. Now remember, an average cost is going to be the total cost divided by the number of units that we produce. Okay, so we first calculate C of 40 and then divided by 40. Well, C of 40, we could also C of 40 divided by 40 equals 23. Now this is confusing me why it says this like this. C of x over, so it's 400 over 40. I don't think this is right. This should be 40 in the middle. I think this is a mistake here. Because if I plug in 40, 400, oh I see, 400 plus 40 plus 0.3 times 40 squared divided by 40. They've already, sometimes when I copy these down, I'm sorry, it doesn't make sense to me. But remember here, we get 400, so 400 over 40 plus 40, because when we plug in C of 40, we get 40 here, and 40 over 40 is 1, plus 0.3 times 40 squared. Well, 40 squared divided by 40 just gives us 0.3 times 40. So when we do this out, we get 23. Notice this is two different concepts. Here we have the average cost per lamp, which is just an old algebra formula or basic arithmetic that we know about average, right? The average cost per unit is the total cost divided by the number of units. The total cost divided by the number of units. So it's C of 40 divided by 40. Here the average, this is the average total cost. So this says if we make 10 lamps, how much would it cost? 11 lamps, how much would it cost? 12 lamps, etc., all the way up to 20. We would add all those totals together, and then we would divide by the number here. And if we did that, we'd get the average cost would be 485. So this is the average total cost, not the average cost per unit, okay? You are used to, in most cases, doing the average cost per unit, the average per test. You add up all your test scores, divide by the number of tests. This average total cost, or this average value of a function, is the average total of that function over that interval. Okay, so be careful there. This is what you're used to, is the average cost per unit, calculating the mean. This new thing is an average total functional value over an interval. It's a little bit different, so I want you to understand that clearly. Okay. So again, here's our formula, the average value. The mean value theorem says if f is continuous, then there exists a number c in AB such that f of c equals the average value. Again, this is just saying what is that total average value over the function from b to a. Okay? So this is just doing some algebra too, and it's just saying that the area under that curve is equal to the average value times the height, and this is how we came up with the formula. So the width times the height, the average height. Okay?